Can you get recording as well, session?
Yeah, so we're recording. We'll try to record everything. Okay, this is the recording.
Yeah, recording. Yeah, recording is going. So let's start the main topic. Today we're gonna cover basic basics of deep learning. Sorry, the main concepts and what is deep learning in general. So, what is deep learning? Basically, deep learning is all about deep neural networks, and deep neural network is just some function which has some input data and uses this input data to produce some output data. And the idea is that this deep neural network should approximate some mapping F of our interest. So we have some mapping F that we want to approximate, and deep neural network tries to get the same output. If F at X is equal to Y, then DNN of X should be as close to Y as possible. Here are some examples of what deep learning can do. For example, there is object detection. You have image as input data, and you want to detect objects on the image. Where is the cat? Where is the dog? Or maybe something else on the image. There is translation. You have text in English and you want to translate it to French. There is speech to text. You have audio and you want to convert it to text. Image generation. You give some text prompt and you convert the text prompt to images. As I said, deep learning models can play chess or other games. And there is some complicated biology stuff that I don't understand, but it's possible. Yeah, there is one remark here that you should think about tasks, not only about domains. What I mean? We received a lot of requests for deep learning in biology, or for deep learning in computational biology, or some time series. And what I want you to say is that don't focus on the course exactly about, for example, deep learning in biology, because you can listen to other courses and they will be still useful to you. Why? Imagine you want to classify dogs and cats, yeah? Or you want to classify diseases, illnesses of plants. So there is one plant with one disease, another plant with another disease, and you want to understand which disease this plant has. Or you have some texts which are from different categories. One text is about sport, one text is about IT, one text is about something else, and you want to classify whether this is a text about sport or text about IT. Domains, the input data is different, but the main idea of how you solve this task is exactly the same. You have some input data, you have your model, and your model outputs one of the n classes. That's all. So if you want to classify plants, you don't need to learn how to classify plants. You can learn how to classify anything and just apply the same concepts to classify plants. The same idea is about time series forecasting, which was also requested. It's here on the second row. Music generation, or creating a supplement to music part. You have like 2 bars of music and you want to generate the successive 2 bars, yeah? Or LLMs, text generation, Gemini, ChatGPT, they're all based on the same concept of after regressive modeling. You have some start of a sequence and you predict the next token, the next element of the sequence. Nothing harder than this. Or generation via diffusion. You have some noise. You can generate images from this noise, or you can generate some music, speech from this noise, and your model just uses noise as input, produces some output. And the main concept is the same for images and for audio. You can check this to companies here, Stability AI and Refusion, if you're interested what's how do they work. So yeah, the general concepts are identical for different domains. And you can use knowledge from other domains to improve models in your specific domain. You learned how you classify cats and dogs. Now you can use the same techniques to classify texts, to classify plants, to classify everything. You know how to auto-generate music or text. Now you can forecast time series. And basically, in practical deep learning, you can do good publications just by using this. You can find a paper which applies such one technique in one domain, take this technique to your domain, to your specific task, maybe incorporate some new domain-specific knowledge, and now you have your own great publication with ease. Maybe some more examples. Transformers, which are the main idea behind ChatGPT and all this LLM stuff, were originally designed for texts, but as we'll see during second, third, and maybe this week, transformers can be applied in images, they can be applied in audio, almost everywhere. So you don't have to go and listen to courses only about text. It's beneficial to go to courses and listen to courses about audio, images, and all of this. And I'm saying this because many of you requested to go only to CV or only to text or only to audio, but it will be beneficial to you to go to all topics that we are covering, because maybe some interesting ideas that will be useful for you will be covered in audio, and you can then apply it in some other domain, or maybe it will be covered in CV and so on. Coming back to deep neural networks. So inference or application of your model is easy. Given some input x, you return the NN of x. But remember that the NN of x tries to approximate some y. You need to model the NN somehow, so this approximation is good. The process of changing the NN in such way that this approximation becomes good enough is called training or optimization. One remark, what is deep learning in comparison to machine learning? So basically, they both do the same thing. The difference is in algorithms. Deep learning is mostly about neural networks, which can be seen as computational graph, as we will cover a bit later. And neural networks can extract meaningful, complicated features on their own because they have huge representative power, and given a lot of data and long training and a lot of compute, a lot of GPUs and servers, neural networks can do everything on their own. But machine learning, such as linear logistic regression, decision trees, boosting, random forest, SVM, GMM, and some other algorithms, are relatively simple, and they're relatively easier to interpret, to understand how they work, how they perform, and what is the theoretical reason why they work. And they usually require good handcrafted features to perform well. So you can't just use a raw waveform and pass it to logistic regression, and because you want to get a good result, or you can't use image directly. Yeah.
What do you mean by relatively simple?
I would say there is nice theoretical justification why it produces something, and you understand why it works good enough in some domains and some tasks. I would say like this.
Yeah, I guess it's maybe like the architecture, the way it's put together is simpler. Because I guess in these deep learning, there's lots of like intricate components. It's hard, as you say, they don't have a theoretical justification.
Yeah,
But sometimes it actually can be easier to use the deep learning than the machine learning because the way that, let's say, tools expose them.
Yeah, deep learning models can be, we'll repeat to Zoom the question. So the question is, what do I mean by relatively simple? And I mean that there is some theoretical justification why these models perform good in some cases. And you can understand how this model works. But for deep learning, it's not always the case. And that's why there is the explainable AI, which we'll cover in the third week. Because deep neural networks are so large, they're so complicated in their structure that it's hard to understand how they make decisions and why they actually work. Actually, as far as I know, there is no like a good paper which will strongly theoretically justify why deep learning actually work so good. Yes, yeah.
Say big data, how big should be a data to fit to deep learning model?
It depends on the task. Yeah, repeat to Zoom. So the question is, when I say a lot of data, what do I mean by a lot? It all depends on the task, but usually the more data you have, the better your model will perform. And if you have too small amount of data, maybe that's the reason why your model doesn't work. Yeah. So I said that, yes, sir.
One question. How do you know if you have to apply machine learning or deep learning?
So if you use one of these variety of algorithms that I mentioned, then you do machine learning.
Depending on
Depending on the algorithm, yeah. Deep learning is only about neural networks, which will be can be treated as computational graph, as we'll see, and machine learning is everything else. I would say like this. Yeah, no questions. Good. So moving on to training. As I said, in order to get good approximation of your function, you need to train your model or to optimize it. Training deep neural networks is an iterative process. So given some total number of iterations, the training scheme can be summarized in 3 simple steps. First one, you get data, which you're gonna use to train during this iteration. Then you have forward step. Given your model and input data, you produce output and calculate something which is called loss. We'll cover it in the next slide. And given this loss and your model, you do so-called backward step, which updates your model and makes approximation a bit better. One iteration again. So in forward step, you have input data, you have your model, and you have model output. Also, you have desired output. That's ground truth, y, which you want to approximate. You use model output and desired output to calculate loss, also known as error, which is some measure of how close your model output is to desired output. So it's some measure of similarity between these two. And given this loss, you compute gradients, some calculus stuff, and update your model. These gradients are passed to your model, and your model results in a new model with new weights. Let's cover each step in details. So first one is get data. It's about data set. Data set is a set of data that you use to train or to evaluate your model. If the data set contains ground truth outputs, the task is called supervised. So if you know this ground truth y, it is a supervised learning. It is called supervised learning. Sometimes you don't have this y, and there are self-supervised models, unsupervised models, but we won't cover it during the first week. We will have a bit about this, I guess, during the second or the third week. So for now, when I say data, I always assume that we know the ground truth output. So you can't use just your dataset, your full dataset to train your model. You should split it into train partition and testing partition. Train partition is used to train your model, and testing partition is used to evaluate your model to measure how good the performance is. Why you can't use the full dataset? There are 2 reasons for this. The first one is that it is impossible in reality to get all possible input data. Imagine you have this function in gray, and orange dots are your data sets which you use to train your model. Maybe your data set contains samples from the left picture, or maybe it contains from the right. You can't get continuum elements. You can't get the full x-axis because it's just infinity number of elements. And depending on this training set, you might get different trained models and therefore achieve different deep neural networks. Moreover, the second problem is that in reality there is noise. So maybe there is ground truth Y, but it's usually impossible to get real data with exactly exactly true ground truth. There is always some noise. Like you imagine you want to predict, I don't know, the money that someone gets. Maybe you get exact total number, but maybe you have some plus minus 0.5 to this number. So there is always noise. And as we see here, the true line is gray, but elements sometimes are a bit above this gray line or a bit below this gray line because of this noise. Yeah. So if you have these true problems, you can get one of two things. First one is called underfitting. Basically, your model is so bad that it doesn't approximate your function at all, even on the training data set. And another one is called overfitting, when it approximates your training set so well that the error is almost zero, but the function is actually far away from the real function. As you see here, this orange line is far away from the gray line, but in terms of training data, these orange dots, it fits perfectly well. So if you have this model on the right, and you use only training data, you can think that your model is great. But actually, it is a bad approximation. So the splits are required to answer the question how good your model really performs. You cannot use training data to do this because your model has seen this data, it knows it, and it knows what to predict to get small error. But on unseen data, it doesn't know how to do this. So real performance assessment should be done on this test split. Coming back to this orange model, imagine you have this test data, which is in green. And you see here that if you measured performance on green data, you would notice that your model is actually bad because the error here, the performance for these dots is, and for these dots is really bad. And if you want to compare different models, imagine you have this black one. Maybe it has worse training performance. It doesn't fit these orange dots so well, but it's much closer to the gray line, and it has much smaller error on the test data. So if you want to choose between black or orange one, you should choose the black one because it actually does better approximation. One remark, sometimes you may have three splits. Training data, which is used to train your model. Validation, also known as development set. There's unseen data that you use to choose the best model. So it's also unseen data, but you make choices which model to use as your final one, which model to use in your production. And there is test, also known as evaluation set, which is used to evaluate performance on unseen data, and you don't use it to make any choices at all. So the idea here is that choosing one model within several ones is a bit of cheating. So if you have only two sets and you chose your model according to test set, maybe you choose maybe a model performs good on a test set, but it won't perform good on another unseen data set. So validation here is required to avoid this cheating. You make choices on one partition, but you understand whether your choice is really good, whether your model is really good, or whether you just did a great choice according to comparison to the test set. Okay. Yeah. because the data is unseen, the performance on it might be much worse than on training data. As we saw this orange line, it had much worse performance. So to mitigate this problem, there are several generalization, also known as out-of-domain techniques. And one of these techniques is called data augmentation. What it does, it corrupts your input a bit, so you still can predict the output, but the distribution of your input data shifts a bit. For example, you have this dog on the left. You as human know that this is dog. You can erase its face, and you as human still know that this is dog. So maybe it's reasonable that your deep neural network should also know that this is dog, even if you don't have dog face. Or you can slice, you can crop part of the image. You as humans still know that this is dog, or if you apply some water filter, you as humans still know that this is dog. So these augmentation techniques are applied to make your deep neural network more generalizable to unseen data, because you can't get all possible photos of dogs. You can't get all possible variations of these dogs, and you try to make some synthetic versions of them, so your model doesn't just learn the training data, it actually tries to understand what in dog makes it look like a dog. Yeah, so there are some more examples here, and in all of them, you as human know that this is dog. So a good deep neural network model should also understand that this is a dog. Moving on to models, we covered the get data iteration. So deep neural networks can be seen as computational graph, just stack of layers that return new output given the outputs of the previous layers. In these examples with 4 layers, you have input data. Layer 1 gets this input data and returns output to layer 2. Layer 2 uses output from layer 1. Layer 3 from layer 2. Layer 4 uses from layer 3 and layer 2. So it is possible that your layer can use output from several previous layers. And layer 4 produces the final output.
So for this model, if you want to output the data, which layer it should be?
Input data. Yeah. So you always augment input data. It is possible sometimes to augment some intermediate layer, but you should understand what you are doing.
I guess one way, like your erase thing, would be kind of the equivalent of dropout in intermediate layers.
Possible.
But I guess what you would do in intermediate layers would be called more regularization rather than augmentation.
I can give you an example, but I'm not sure that everyone will understand it. But let's try. So if you don't understand it, don't worry, like you will understand later, but just to use an example. Imagine you have a model that given some mix of speakers, like if we are going to talk in this room all together, there will be plenty of speakers, and you want to extract only my voice, for example, or only Eric's voice, yeah? And also, apart from separating these audios into unique utterance with only one person, you want to get a text transcription of this utterance. So you want to get the speech signal and the text signal. And how this is sometimes done, there is one model that returns speech, and you integrate another model that returns text somewhere in between. And in this in-between part, you can augment the data which is going to this second branch with so-called spec augment, which deletes some part of rows or columns in the images. So if it's too hard, don't worry.
Maybe you can use the whiteboard next time to explain things. Maybe you can, I don't know if you want deeper analysis of that.
Just so everyone understand. I don't know if you can see it here, but here is your audio. You want to return audio, you want to return text, and you can do augmentations here. or you can do augmentations here, but only for this branch, not for this branch, only for this one. For the branch that wants to return my text. For my voice, there is only one augmentation. Yeah, so one layer, all it does, yeah. How we choose the model for validation? Yes, that's the question. So to choose this, you have several metrics, which are task specific, or you can use directly your loss on this validation data, but it's not usually a good choice for making decisions. So we will cover this, I guess, maybe on Wednesday.
Maybe for a concrete, like an easy example, like classification, you know, you have 10 classes. You have your computing and accuracy and your train. And what Peter was saying, you don't want to pick on that because you could be overfitting, but you're going to classify on your validation. And let's say whichever model gives the best validation, classification, accuracy, we'll take that model. So in that particular application, you're using like accuracy. So how well it's classified between classes.
Yeah, I'm not sure that Zoom people heard it. So let me repeat what Eric said. So yeah, imagine an example of classification. There is such thing as accuracy. Basically, it means how many classes, how many images you classified correctly. You know, like this is a dog, but your model says that this is a cat, it's a wrong classification. But if it says that's a good classification, that's like 1. And you sum all these correct classifications, take the average, and that's your accuracy. And you choose the model which has the best accuracy, because accuracy is a reasonable metric for classification to make decisions. Loss, not always. And depending on your task, you may have 1, 2, even 5 metrics. And maybe for some metrics will be better for one model, some for some other model, and you should decide which metric is more important in your case.
In the past, that would be later. We use more metrics, but in the validation, we choose one.
You should calculate several metrics on validation data just to understand how it performs. So maybe if your model is better only in one metric, but is worse in like 10 other metrics, maybe it's not a good choice. And if another model is better in 10 metrics, but worse in primary metric, maybe it's still a better model. So you need to decide like how, you need to decide yourself, or according to some papers in your domain, like, do you want to get this exact metric to be as high as possible, or do you want to have metrics in average as high as possible, and so on. But in general, the idea is that you calculate some metrics to make decisions.
Retesting, but because if we test everything in the validation, but not complete the purpose of it.
You test everything on validation, and you make choices. On test data, you doesn't make any choices. You're like, imagine you created a model in your company. You can't choose your model after you published it to your to users, after users see it. After users see it, you might achieve some worse or greater performance, but you can't make choices anymore. So validation is you have your data in your company to make choices, and test data can be seen as the data which you will work on some afterwards, and it is not possible to make any choices anymore.
I'll make a comment. I'll mute myself on Zoom
Here, so that'll be strange. You muted yourself. Okay.
Yeah.
So I guess what you're getting at is, why do we need a test set sometimes? Because there's sometimes this philosophy, okay, maybe you don't need a test set, and some people actually just do training and tests, so they remove the validation. I think in research you'll see that also in some companies I worked at. They just say, okay, we're gonna have a train set, and we're just gonna have one unseen test set, and that's what we use to just deploy. Because usually, sometimes you'll find yourself in a situation where you don't have enough data. So making a third data set will kind of remove the amount of data you can even use for training. So some people will just do 2 sets, train and test.
Okay.
Be fine. It's okay.
Yeah.
Yeah, because my mouse.
Right. Okay, so hello everyone. I'm Atli. I work on deep learning optimization actually, and I'm going to be covering this in a little more depth. So just maybe to like recap a little bit of what like Peter said, like in deep learning optimization, we are trying to find a model to predict some data. The model is a function of two things. First is the input to the model, and then the parameters of the model. And our goal in optimization is to find parameters that allow the model to classify the data correctly. So I'm going to be using very kind of like simple toy models to explain this. These are not going to be like real neural networks because it's very hard to sort of like visualize neural networks, but the insights should pretty much like generalize to neural networks. So here we are just going to be looking at a data set shown here to the right with two classes like red points and blue points. And our model is this simple function shown here, which basically defines some line on this plane, and we are going to classify points on one side of this line as red and blue on the other side. And our goal then with optimization is to try to find these parameters that describe this line, like this angle theta and this bias b. That gives us the best classification. Like I said, this model only has two parameters. Neural networks typically like start at like maybe tens of thousands, go up to like billions. So it's like we can visualize a lot of things in these low dimensions. Most of the insights sort of like roughly will hold for neural networks, but it can also be slightly misleading sometimes. The goal of this is mostly to give you some sort of like insights into optimization. A lot of it at the end, I'm just going to give you kind of like concrete recommendations that you should probably just take and apply to your projects. It's not that easy. It's not that hard to get like a good optimization setup, but it's also it can be easy to screw it up. And if you screw it up, then your final performance will like really suffer. So it's good to just like follow these guidelines that we'll give. Okay, so this is the kind of like the toy example that we are going to be looking at. I'm only going to be looking at the training loss essentially. So I'm only going to be concerned about the points that we actually know here. In reality, like Peter mentioned before, we might want to test on some other points that are unseen, like the arrows and the question marks there. But in practice, this model can't really overfit. It's so simple that like, yeah, you won't have any what we call like generalization issues. Okay, so how do we optimize these models? We do it through variations of what we call gradient descent. Okay, and maybe first of all, like, how do we go from our function to actually get predictions? So we had two classes that correspond to like 1, which were the red points, and 0 for the blue points. But our model actually outputs a continuous variable. And typically for classification, we're just going to take the closest class. So here we can basically look at whether the output of our model is larger than 0.5, like which is right between the values for the classes, or smaller. And depending on this, we will classify points as either like red or blue. In sort of like slightly mathematical notation, we use these like indicator functions, which basically take the value 1 if the condition in the subscript is satisfied, or 0 otherwise. Okay, and what we maybe actually care about is just the accuracy, like Peter mentioned before. Basically, like how many points do we correctly classify? What fraction of the points is correctly classified? And here we have some data set that we are going to denote as D. And this absolute value of the data set is actually the size of it. And then we just sum these predictions over the entire data set and measuring with an indicator function whether it's correctly classified or not. However, we can't actually optimize this function directly. So the reason for this is that it's essentially not differentiable, which tells us that like for a given parameter values, there is no signal to tell us like how to change them. So we could try all combinations and select the one that like performs the best. But in practice, we can only do this for sort of like small scale problems. For neural networks, this is impossible. So we really have to get some sort of like signal for given parameters, like how do we update them to get like slightly better predictions. And this is where what we call a loss function comes in. So a loss function is actually going to compare the continuous outputs of the model to our desired outputs. And here we are just going to use this like squared loss. So we're just going to take the output of the model, subtract the prediction that we want, which is given by y, and then we're going to minimize this. And the hope is that by minimizing this, our model's outputs will be close to 1 when the desired class is 1, and close to 0 otherwise. But this is not always true. So it's just a rough. We hope there's a correspondence between the loss function and the accuracy, what we really care about, but it's not 1-to-1. But generally, if we minimize the loss function, we'll kind of also be performing better on the accuracy or whatever metric we actually care about. Okay, and how do we actually update our parameters? We are gonna look at what we call a gradient. A gradient is just a vector of the derivatives with respect to each parameter. In our case, we only have 2 parameters, theta and b. So the gradient is just a vector of these 2 derivatives. And then we are going to be updating our parameters with a simple rule. We basically take some current value of the parameters. We compute this gradient, and then we're just going to subtract some multiple of the gradient from the parameters. And we're just going to repeat this until we hopefully get a lower value for the loss function. Okay. Yeah, and we can basically visualize this. Oh yeah, this is the learning rate. The scaling factor is the learning rate. This is a hyperparameter, which is basically just a value that you specify yourself. There is no gradient for this or anything. This is a choice that you have to make. This also comes into why we use validation sets versus like training sets and so on. Because generally on the validation set, we can measure how well a given learning rate is performing. And for validation, we can then use basically a test set to measure like how well it would perform in the wild. Because by choosing the learning rate, let's say especially for the data set that is not too large, you could make like a really good choice of the learning rate that like kind of, you know, optimally performs on this like validation set. But because you made choices on the validation set, your performance on like new unseen data that you didn't make any choices on can be worse. Okay.
Maybe one terminology we can give here is hyperparameter.
Yeah.
So this is like what you were talking about, like hyperparameter tuning. And if you do this on your validation set, you're kind of corrupting the purpose of your validation sets.
Yeah, I mean, I would kind of say this is what we hope to get with the validation set is to make choices, because on the training set, you just massively overfit. So you want some sort of like generalization, and you get a rough idea of the generalization, which depends on the hyperparameters by looking at the validation set. But you can still be performing much better on the validation set than you would on completely unseen data. So to measure, like, before you deploy your model out in the wild, you want to have some idea of like how well your model is going to be performing. You should really measure this on a test set. Okay. Yep.
If D is finite, what is in the middle?
How can D be?
So I imagine D is just like the set of data we have and the output,
Mhm.
and then so like it's F differentiable or
Yes. So the question is, if D is finite, is F differentiable? And yes, essentially the loss will be differentiable even for like a single sample. Like this loss function will be differentiable, and then like the full loss function is just the sum of these like individual losses for each sample, and each one is differentiable. The sum of them is also going to be differentiable. Okay, so we can visualize this basically an animation for our tests function. So here, what I'm doing is I'm plotting the loss surface for this for this model and data set. So here on the left, we basically have the value of the loss for a bunch of different values for the parameters theta and b. Yes, there's a question.
I had a question. The sponsor stands for different learning rates.
Each.
Sponsor, like in the on the left.
Okay, no, it's actually for each value of the loss. So the colors correspond to the value of the loss, and the contour lines, which is shown in black, are lines that show where the loss is equal. So along each of these lines, you have an equal value of the loss. So you can kind of visualize this as a 3D surface where the color kind of tells you about the height of the value there. And then like the contour lines would basically show you like lines that are like flat in the surface. And yeah, on the upper right, I'm basically showing us for the given value of theta and b, our parameters, what would the prediction of the model look like? So we are showing the original data set points in red and blue, and also the prediction of the model, which are these like shaded regions. So the model is predicting everything that is shaded red will be classified as positive, and everything that is shaded blue as negative. And you can see at initialization, our model is really bad. We are basically incorrectly predicting like almost all the points. Then in the bottom right, I'm showing the loss over time. So I'm going to show you like how we'll update our parameters over time, and at each step we'll observe some sort of loss. And in practice, for a neural network, you cannot at all like visualize the loss surface or the decision boundary, but like what you really see during your optimization is this are these loss curves. So for higher dimensions, that's really all we can see. But what's going on under the hood is something like we're showing here for like these simplified models. And okay, so here we start at the white point, and what I'm showing with the red arrow is basically like what the first update is going to be. And note that this update is going to be, it points in the opposite side to the gradient. So at each point, the gradient is basically going to point in the direction of the steepest increase. But we want to minimize the loss function, so we are doing gradient descent. We're going to follow the negative gradient, and we're going to scale it by the learning rate, and we'll get some update step. Okay, so now let's just see how this progresses. So as you can see, over time, as we perform these steps, we are going to move towards the low portions of the loss surface, basically minimizing the loss. And as we minimize the loss, our predictions are becoming better and better. as we would hope. All right, maybe, yeah. Not zero, but quite low. So this model can actually not achieve zero loss here or perfect accuracy because this line can basically not like classify the data set.
Yeah. So I guess I can't understand the it kind of looks like we got zero in that circle.
Yeah, maybe look at the loss curve to the lower right. It's like it's a low value, not exactly zero. Yeah.
It is clear that stuff. I wanted to understand. It's different because of the the dissociation between the loss function and the
yeah, that's a good observation as well. Like oftentimes we can get like perfect accuracy, for instance, even without the loss of even without the loss being zero. And this especially happens with neural networks because they have so many parameters. They can often easily overfit our training data, which basically means 100% accuracy already, but the loss is not necessarily exactly zero. Okay. So moving on, hopefully. Yeah, in practice, we don't use exactly gradient descent. We use something called stochastic gradient descent, or SGD. And we do this in order to basically make optimization cheaper, because it's very expensive to compute the full gradient because you need to iterate over basically all the points in your data set. And especially for deep learning, your data set can even have like billions of points in it. And and even just like getting one gradient value could basically take forever. So instead, we use a stochastic gradient descent, and what we do there is that we pick a random subset of the data set, which we'll denote as B here. And then we'll basically use B for this iteration instead of the full data set D. So we will compute the loss on the subset of the data set. We'll compute the gradient on the subset of the data set, and then we'll use this gradient for this current subset of the data set to basically update our values as before. And this can be, for each iteration, this can be much cheaper, like millions of times cheaper easily. And the hope is kind of that, like, even if the resulting gradient is not the exact gradient, it's close enough that like we'll still make progress that is oftentimes like even almost as fast as we would otherwise. And yeah, just to emphasize that we can view this like mini-batch gradient as a true gradient plus some noise. So we'll often view this as basically the exact gradient plus some like random variable that like describes the noise. And we can visualize the stochastic gradient descent as well, basically in the same way. There are a few changes here. On the loss surface is the same as before. On the upper right, I'm still showing the decision boundary and the original data points. I'm also showing the mini batch at each iteration. Here we are using a batch size of 4, which describes the size of the mini batch. It's another hyperparameter that you need to choose for your optimization. So the mini batch is denoted by these like black circles. So that's basically the data set that we are seeing in each iteration. And on the lower right, instead of one loss, we now have basically 2 losses. We have the loss on the full data set, and we have the loss on the mini batch. Now, since this gradient is a noisy estimate, on the loss surface, you will see that like the direction of the update will not always kind of be in the direction of the gradient, but the gradient itself would always be orthogonal to these like contour lines that are shown. But as we will see, like when we do these updates, sometimes, yeah, like this step, for instance, is in the opposite direction. So on the full data set, in this step, we're actually moving away from the minimum. But on average, we still make progress, towards this like minimum. But here we are using maybe like 4 points at each iteration instead of 100. So it's like 25 times cheaper each step. Okay, and as you can see, towards the end, if we look at the entire trajectory, this, yeah, no, you can see the noise. The trajectory is very noisy. It kind of like just, you know, especially in the flat region, it's just all over the place. But in the end, our final loss value is actually very similar to what we obtained with full gradient descent. And we are kind of classifying the points roughly correctly. Okay. Yes. Yes. Okay. So the question is, does the size of the mini batch depend on what kind of problem we have? And the answer is basically yes. So there is like a maximum kind of like practical mini batch size that you can use. This depends on the hardware that you're using, the model that you're training, and so on. It also depends on kind of like statistics of the data set. So larger mini batches will really only be sort of effective up to a certain size. And after that, like even if you increase your mini batch size, your gradient estimate is not really going to get better. And then it's just like wasted compute. But generally, for like the fastest training, like mathematically, like the optimum mini batch size is 1. But in practice, when you're using something like a GPU and so on, there are other factors that you need to consider. So oftentimes, like GPUs are actually more computationally efficient at like larger mini batch sizes. So maybe on a GPU, computing a mini batch of 1 versus a mini batch of 1,000 actually takes roughly the same time. And then a mini batch of 1,000 overall results in much faster optimization. But in general, yes, it's a hyperparameter, and you should absolutely like think about how you use it on your problem. Okay. So how do we basically obtain these gradients? And as Peter described a little bit before, we are going to do this in 2 steps. First, a forward pass to obtain some sort of like loss, and then a backwards pass to obtain the gradients. On the forward pass, it is really beneficial to view these models as computation graphs, like Peter also mentioned before. Where here we have like the black boxes denote essentially operations. And the blue edges sort of represent like intermediate values in this compute graph. The parameters that we're trying to optimize are the yellow circles. Our inputs are the gray dots, and the desired output is Y. And we break this like somewhat complicated expression on the bottom into this compute graph. We do these operations basically like 1 by 1. So we obtain like intermediate values. So here, like this first one is really not doing anything. It's more relevant for the backwards pass. But then we just take here the value Z1, we apply cosine to it, and we get some output like we call Z3. And then we just continue this until we get a loss value. This is exactly what PyTorch or any deep learning framework is going to do behind the scenes. But in practice here, we are showing this for like scalar values. If you view a computation graph in PyTorch, it will typically be on like matrices or something like that. So the operations would be something like matrix multiplication rather than maybe like, you know, scalar additions like we're showing here. So once we've done the forward pass, we will obtain the gradients by basically like stepping back through this this compute graph. And this is something that we call a backwards pass or back propagation, and that's essentially reversing the computation of this compute graph to obtain the derivatives of the parameters that we want to update. And we are going to be using the chain rule from like calculus to basically go backwards through this graph. So I'm not going to say all the steps here, but you can kind of see like, okay, we are going to be computing these like delta values for each intermediary value shown in the graph. And this is just the derivative of the loss with respect to this intermediate value. And for the first node, this we can just do some simple manipulation here and get a value that is like two times this like forward value that we had. This is E9. Then for the next one, we basically want to do a similar thing. We want to compute the derivatives with respect to the inputs. We can rewrite this with the chain rule as a derivative of the outputs with respect to the loss, the derivative of the loss with respect to the output times the derivative of the output with respect to the inputs. And this allows us to basically get an expression for delta 8 expressed in terms of delta 9. And then we'll basically just continue this. We use a chain rule at each step, and eventually we have gradients for the entire parameter set. Okay. In practice, you don't have to do this. PyTorch will handle it for you. So we just have to specify the forward pass. PyTorch will handle the backwards pass unless you're doing something really weird. But this is exactly how we do this in PyTorch. So we just import PyTorch. We define our parameters theta and b. When we define these tensors, we need to mark them as like required gradients. And once we mark the tensors like this, PyTorch is automatically going to figure out like how to create these compute graphs and back propagate through them until you reach the values, the gradients for these parameters. We define some inputs and labels. We don't need gradients with respect to those, so we don't need to mark them as requiring gradients. Then here on this line, basically we express the loss. PyTorch is going to figure out how to make a computation graph for this, which is basically going to look exactly like the computation graph I showed you before. And instead of having to manually figure out how to do the gradients, we just call loss.backward, and you'll get the gradients. PyTorch is going to fill out these fields on both theta and b, which give you the value of the gradient. And then we could use this to update the values if we wanted to. In practice, we typically abstract this on a slightly higher level, and you don't even have to do the update yourself. You can just call a function that PyTorch already defines. Okay. So as I mentioned before, we have this hyperparameter we call the learning rate. In practice, we actually vary the learning rate over time through optimization, and this is really important to get like good performance. This function of like how to vary the learning rate over time, we call a learning rate schedule. This is very important for stochastic optimization. It's less important for like non-noisy optimization, but still important. The theoretical reasons for this are slightly complicated, but we can still see this like, with an example why this basically matters. And we are going to be looking at this simple function here, which is a function of two variables, x and y. Here you should view x and y kind of like as the parameters that we are optimizing, not inputs or labels. So the goal is to get from this like starting point that I show here with an x to the minimum shown with the pink star. And again, this is the same type of loss surface as we visualized before. So we have the loss in different colors and the contour lines in black. And it's important that like we have this function, then I'm going to add some noise to it, to the gradients to basically get a simulation of stochastic gradient descent. Okay, so if we try to optimize this function and we just choose a constant learning rate and this learning rate is low, what will happen is that we actually kind of quickly get to a good value for y, but we make very little progress in the other direction, because at each step we are basically making very small progress along the x direction. But we actually get pretty close to y, because lower learning rates are good at getting rid of this like noise that comes from stochastic gradient descent. Okay, so yeah, maybe I'm showing three things here. On the left side, we have the learning rate schedule, which here is just a constant value with a low learning rate. In the middle, I'm showing the trajectory if I do 100 steps of stochastic gradient descent. And on the right, I'm showing the resulting loss. And here, there are some minor important details. On the right side, I'm showing two things. I'm showing an average over like many different experiments, and I'm showing an example of one trajectory. So the one trajectory kind of looks a little noisy, and the average is solid. It looks much smoother. And in high dimensions, the noise will behave slightly different. So essentially, these fluctuations will be smaller, or at least they will not get you as close to the minimum. So maybe you should mostly be looking at the average. It'll give you a better picture of how this works in high dimensions. If we instead choose a high constant learning rate, we'll minimize x really well, but due to the noise in each iteration, we'll actually not get close to y is equal to 0. And basically your loss will flatten out at some level, and even if you continue this forever, like your loss value will basically never go below this this threshold. Yeah,
Maybe we should say that if you make it even higher, it's possible that your loss will go up in another direction, like it will only increase and not decrease.
Yeah, exactly. So yeah, these learning rates are what we call like stable, that they will not result in your loss going to like infinity or something like that, which can also happen if your loss is too high.
Yeah. So if your loss goes up, try to make learning rate smaller, and maybe that will fix the problem.
Yep. And in between these values, we have some sort of like trade-off that makes decent progress along both directions. So we can actually roughly minimize like both x and y, but we still have some basically noise at the end that like prevents us from getting to y is equal to 0. But you can see that this intermediate value is actually better than both like low learning rates and high learning rates. But if we use a schedule, we can kind of get the optimization to work as both having high learning rates and low learning rates at the same time. So here we are showing what we call a cosine decay schedule on the left. It's shown in green. So it's basically an offset cosine that goes from some maximum value to a minimum value. And we'll go into some more details later. But essentially, when the learning rate is high early in training, we'll make good progress along the x direction. So we'll get close to the minimum. And then towards the end, when we have lower values, we'll kind of eliminate the noise and actually get pretty much exactly to the minimum. The loss is actually really close to 0 here at the end. So the takeaway here is just use learning rate schedules. It's very important for optimization. And we'll even iterate on this a little more later. Okay, yeah. So sorry, how we choose which one? So in practice, what we really use for, yes, so the question is about sort of like other optimization methods like conjugate gradient descent or or regression. And in practice, some of these don't work with noise at all. That's actually fairly common for some methods. And sometimes it's just too expensive to do for neural networks, or we don't have the kind of closed form solutions that we require for some of these. So in practice, basically, if you optimize neural networks, you always use stochastic gradient descent or some variation of it. And there are no other optimization methods that we have gotten to work well for neural networks. Okay. So now for some just practical advice. So in practice, we are going to be using slightly more complicated methods than gradient descent. We're going to use some variants of gradient descent that use additional tricks that basically perform better in the end. What we recommend is this optimizer called RMW, and you don't need to know maybe like all the details of this. You can pretty much use it as a black box, but essentially it has 3 additional tricks for optimization beyond what stochastic gradient descent is doing. We have this thing that we call momentum, which is essentially instead of using the gradient to make each update, we use some sort of like smoothed out history of the gradients. And this really helps when you have little noise in your optimization, basically when you have large mini batches, but it's also not harmful if you have smaller mini batches. So basically we recommend using this always. We have another trick that instead of taking the magnitude of the gradient, we basically normalize the update size with also a history of the gradients. So in this sense, we can, for instance, like scale a gradient or scale a loss function by some constant value, and our update sizes will actually look the same as they would for any other scaling of the loss function. This really helps with certain types of architectures and tasks, but it's also not really harmful in other settings. So again, we just recommend using this. It's easier than like figuring out when this is going to work and when not. And the final trick is called weight decay. And the reason why this works is again like a little complicated, but essentially this is going to shrink your weights over time, and this allows the network to learn more effectively in almost all settings. But yeah, the reasons why are actually a little complicated.
Also works as regularization. You know,
That's
that's a lie.
Yeah, that's a lie. Basically, it's not regularization. But yeah, so there is a
common mistake.
Yeah, there's a widely held misconception that like weight decay is like a regularization method. It's not. It interacts with the learning rate in a complicated way. But this is actually a research topic that like both I and some other people here at the EPFL have worked on. But in the end, our recommendation is just use RMW unless you have a really specific reason not to. Just default to RMW. We have extra hyperparameters now, not only the learning rate, but also defining these kind of like momentum, the gradient normalization, and the weight decay. You can roughly get away with the default values of those. But yeah, so basically just stick to RMW. You can even use the default hyperparameters aside from the learning rate, which we'll come to now. So in practice, yeah, tune your learning rate. There is no single good learning rate that is going to work across all setups, and the learning rate typically has a very strong impact on your final performance. So here we are showing what we call a learning rate sweep, where we do optimization with a bunch of different values for learning rate. We run the entire optimization, and we just show the final value that we obtain at the end. And it often looks something like this. There are some good learning rates in the middle. Learning rates that are too high or too low result in much worse performance. So yeah, I think this is maybe like the single most important thing that you have to do kind of like manually is to tune your learning rate. If you want good performance, yeah, tune your learning rate. Yeah.
It depends.
Yeah, so the question is if you have one learning rate for the entire model. it depends a little bit on how you define your learning rate. But typically, yes, like you have one learning rate value that you pass into this optimizer, like RMW, and we're using that across the entire model. And no. Basically, is it optimal? No. There is almost certainly some scheme that sets the learning rate for each layer or even each parameter in some way. But in practice, we just can't find these settings. So as a heuristic, we use a single learning rate across the entire model. But for something like RMW, it actually scales the updates. So RMW can also kind of be seen as a learning rate that depends on each parameter specifically. But this is not like a head parameter. So like this mapping is like is basically a one-to-one mapping, where yeah, but in practice, yes, fully tuning your learning rate like individually for like each parameter in any model would probably give you better results. In practice, you can't do this.
If I can add, there is a command in fine-tuning when you have your pre-trained model and you add something new above it. So usually you want to use one learning rate for your pre-trained model to make it pre-trained, kind of pre-trained, and to avoid ruining the pre-training, and a larger learning rate for the head. So there might be a case when you use one learning rate for the head and one learning rate for the backbone. But usually, yeah, one learning rate for.
Yeah, that's a good point. Yep.
How many acceptance rates from which you start?
There is a meme Twitter.
Yeah.
There is a meme on Twitter that you should always use a 3E-4. Don't ask why, just like some random guy says this, and everybody on Reddit and everywhere started using this learning rate as a default one.
Yeah. So yes, somewhere like 1E-3, 1E-4. Those are good kind of like starting points. But in practice, this also depends on your batch size. It depends on basically all the other head parameters. So if you're doing stochastic gradient descent at a small batch size, you want to use a completely different learning rate than if you're doing it at a large batch size. And same depending on like how you set your weight decay, how you set your momentum, and all of these others, it'll actually shift where the optimal learning rate is. So in general, yes, there can be like good starting points, but they're typically not optimal. So just do a little bit of like tuning around this. You can even do this on like shorter training runs. You maybe don't need to like run like entire training runs. But yeah, we really recommend tuning your learning rate if you care about your final performance. Yeah.
The larger the batch size, the learning rate, no?
Sorry?
The larger the batch size, the larger that you use the learning rate.
Yes. So the question is, with larger mini batch sizes, should you use larger learning rates? And the answer is yes, typically. It's I might cover this in the distributed training session a little more, but often there is kind of like a linear relationship up to a certain batch size, and beyond that, basically you cap your learning rate at that point. You don't want to go higher on a specific value, but yeah. And yeah, is there another question? Okay. Yeah.
So you switched when you went from the learning rate schedule to this, where you said you took this constant learning rate. So would you use the schedule with LMW?
Yes. So this scales. So the learning rate schedule scales the entire. I guess this hyperparameter is going to change the height of the learning rate schedule. So here we are not using a constant learning rate necessarily. We're just scaling the learning rate schedule by a different value. Yes. Yes, and yeah, always use the schedule still. Yeah, and in practice, we will change the schedule a little bit. We'll now add like a portion at the start of training, which we call a learning rate warm-up. This is another one of these sort of like tricks that are hard to understand, and this actually only applies to neural networks. You can't even, there are no simple examples that show this that I know of, at least. but basically we start at a very low learning rate, basically 0, and then we increase it up to some, like here we increase it up to like 1.0, but like this 1.0 is basically your learning rate hyperparameter, so it scales this entire function. And then we use the cosine decay that we had before to go down to 0 again. And yeah, especially like if you're doing any of these three, like if you have large mini batch sizes, if you're using transformers, or if you're using this optimizer that we discussed before, RNW, you should probably do a warm-up. And we recommend something like 5% of the training duration by default. Even when you don't need it, even if you might be slightly better off in some cases not doing this warm-up, the difference is typically small. So we recommend just like at least starting with this, and then you can maybe check if it helps or not, or if you can get slightly better performance. Okay.
I don't know if you mentioned the term, but what are different terminologies you use for training duration? Is there for iterations?
Yeah. So the iterations is basically the number of steps that you do in like stochastic gradient descent. Sometimes you measure this in like epochs, when it's like, and then it's the number of like passes you make through your data set, but it's just a different way of like scaling this axis. So instead of doing like 20,000 iterations, you might do like 200 epochs, where like each epoch is like maybe like 100 iterations that is sufficient to get through your entire data set. But they're basically measurements of the same thing. And if you do LLM training or something like this, we also kind of want to stick to iterations, because sometimes something like an epoch is ill-defined and so on. So it's but yeah, it's a valid point. Okay. Then in practice, now I'm just gonna show you basically how you do this in PyTorch. You define your model somehow. We'll leave that up to like later sessions to show you how to define different types of models. You will also define a loss function that you want to use that takes the output of this model and creates a loss from it. To define the optimizer, we use this this function call here that is built into PyTorch. So torch.optim.rmw, we give some hyperparameter values here. So you should consider these, especially the learning rate. This may not be a good learning rate specifically. The weight decay and these other hyperparameters are decent here. And there is one final trick with weight decay that like is also like a bit complicated, but we want to split our parameters into two sets. We want to apply weight decay to one set and not the other set. And this basically helps almost always. Again, the reasons for this are slightly complicated, but basically just do something like this, and typically you'll get better performance than if you don't.
Yeah. Moving back to the question you asked about learning rate. So if you want to have learning rate, learning rate for one parameter and another for another parameter, you do in a similar way, but instead of saying weight decay equals 0, you would say like learning rate equal some other value. So it's done in a similar manner.
Yeah, that's a good point. Then once we have this, we have to define our learning rate schedule. Sadly, PyTorch doesn't have this, cosine decay with a warm-up.
One cycle
No,
doesn't work the same.
one cycle changes the momentum as well in a way that like I don't recommend at all.
Okay.
So yeah, sadly we kind of have to manually do this, but this is just boilerplate code. You can basically copy something like this, and in the end you create this like scheduler object that takes in your optimizer and a lambda function that basically gives you the learning rate at each step. So we map from the step to the desired like learning rate, and we have to define this function ourselves. Okay. And then this is how the training loop would roughly look in practice. So we at each iteration, we get some data, we compute the output of the model for this input. So here again, X is the input to the model, Y is the desired target here. I know I've like overloaded this like X and Y a little bit. We compute the loss, which is basically some sort of like comparison function between the output and the desired output. We do this backward propagation. And then to update our parameter values, we call optimizer.step. To update our learning rate, we call scheduler.step. And then we have finally one more thing that basically just resets the gradients to 0. If you skip this step, basically your gradients will accumulate over time. So basically always do this at the end of your loop. Otherwise your optimization will basically not work. Okay, and that's it for the optimization part. Thanks.
Yeah, thank you.
Yeah, we will cover this code part today and on Wednesday, and maybe each day throughout the week. Yes, there was one question in the chat. I don't see it. Sorry, what is pdim and p.dim? I guess this is about this slide. So p here in Python, as you see, is a model parameter, some model parameter, and dim is a shortened version of the dimension, the number of dimensions, and usually bias has only one dimension. So in this example, we define what is biased and what is not biased just by comparison the number of dimensions with one. Okay. Okay. Yeah. So if you haven't understand the theory behind optimization, just keep in mind the main scheme, the schedulers, the Adam, and also look at the code that we will cover today and the next week. They also have some explanations, and maybe it will be easier to understand just by using code. Yeah.
For for example, the bias is not scalar, it's a vector.
If vector is a one-dimensional thing.
Okay, so one. Okay.
Yeah, but maybe some cases your bias might be two-dimensional, maybe for matrices. Yeah. No, it will be.
It's going to be one dimension.
Okay, yeah, in Torch it is always one dimension, so it works. But if your custom layer has 2 dimensions for some reason, just use another comparison scheme. Yeah. Okay. Yeah, let me open the code. One moment. Yeah, so today we're gonna cover the basics of PyTorch. I hope you're familiar with Python or at least NumPy. I send you some links on Luma. If you didn't see them, please see. Also here, this seminar is already available on GitHub. You can download it if you want. And one thing, we won't do seminars like it's usually done at EPFL, like you do your stuff on your own and I'm just sitting here and doing nothing. Yeah, I think that this doesn't work. So the goal here is that I show you some stuff and we are doing it maybe together, or maybe I'm just doing it, or maybe I give you like 2 minutes to think on your own and you will tell me what to do. If we have some parts missing for this seminar and for the second one, we won't have such stuff. So I will just talk, or you can ignore me and just read because I put everything which I want to talk about in text comments here. But yeah, I think this will be more efficient than you are doing things on your own. Yeah. So PyTorch is just one of the frameworks. There are some others like TensorFlow, one of the popular ones. I guess in JAX you can do some similar stuff, but PyTorch is the most popular, and at least for now. And if you want to like read papers and find code that they use, it is better to know PyTorch for now. But in general, they're kind of similar. There is some inner difference between how PyTorch works and how TensorFlow works. PyTorch creates this computational graph on the fly, and the TensorFlow, as far as I remember, compiles this graph, so it like calculates the graph, the whole graph, and then do some stuff. So if you know PyTorch, you will understand how other frameworks work, so don't worry. Here I added some links to documentation, tutorials, and examples. They are pretty good. We will cover most of the stuff during today and Wednesday, but it will be helpful for you to just read this, I don't know, like 6 or 7 tutorials on many stuff. Yeah, so we start with importing some libraries, storage, NumPy just to show that they're similar, some plotting stuff, matplotlib to show some plots. And here are 2 tricks for IPython notebooks. I'm not sure that you know them. So the first one is to use Retina mode, which will make images a bit better in resolution. They will look like Apple Retina, kind of. And Seaborn, just one way to do white grid. Maybe it's overkill because you can do just plt.grid, but I prefer just use CNS and don't care. So in Torch, and you work with tensors. Tensors are like matrices, but with a larger number of dimensions. Instead of having like D1 and D2, you have D1, D2, and so on, up to Dn. These tensors can be in real values, can be in complex values. And you have several methods to create a tensor. One way is to use existing iterable array-like object like Python list or NumPy array, or using some built-in functions from PyTorch like you do in NumPy. Here is one example. Let me run the code. So you have iterable object Python list 1, 2, 3. You use torch.tensor on this iterable object, and now you have tensor which contains the same elements. Okay. Or you can do the same with NumPy. You create NP array from 1 to 3, and you can create tensor from NumPy array. Good. There are also built-in methods which are preferred to save speed, save memory, and increase speed. For example, there is a torch arrange, which works the same way as NP arrange. That's why when you know NumPy, you basically know the basics of creation of tensors and multiplication, all this stuff in NumPy, or sorry, in Torch. Arrange creates, as you see, elements from 0 to up to the numbers that you indicate. Here it is 3. Yeah, we can access some meta information. Here is the dimension thing, which was in the question. So element type is tensor.dtype. Here it is a torch int 64. There are floating points, like floating points is like float numbers 2.0, 2.1. That's a float, and int is integer. There is also support for complex numbers, for Boolean, like true, false, all of this. Size, it is equivalent to the same as dot shape. Is shows us the number of, not the number of dimensions, but the amount of elements within the dimension. So if you have like tensor in D1, D2, D1 is equal to 3, D2 is equal to 2. So your shape will be a 3 by 2. Yeah. So your tensor is a 3 by 2 matrix. So that's the shape of your matrix, the shape of your tensor. So here we have one-dimensional tensor of length 3. You have 3 elements. That's why your torch size is equal to 3. Okay. We can create multi-dimensional tensors. We say that we want to have tensor which has 3 elements in first dimension, 2 elements in second dimension, and 5 elements in fifth dimension. You can do it using tuple, you can do it using Python list, it doesn't matter. You can create full zero tensor using torch.zeros with this desired shape. And as you see here, you have a tensor which contains only zeros. Its shape is exactly as we wanted to, 3, 2, 5. We can create a random tensor using rand n from normal distribution. It looks like this, the same shape, all cool. Yeah, sometimes you may want to reshape tensors, like you have you want to have the same elements but the another dimensions. For example, you have a tensor of size 10, which you created using arrange method, and instead of having one vector of size 10, you want to have a matrix 2 by 5. So to do this, you can either call reshape method or view method. They do exactly the same thing, but sometimes view doesn't work because view works with memory in another way, and sometimes Torch doesn't like when we work with memory in this way. But you can always use a view, and if you get runtime error, change it to reshape. So view is more optimal than reshape, so it's better to use view instead of reshape, and change it only if you have some problems. So we see here that after reshape or after view, we get exactly the same matrix, which contains the same elements as original tensor, but has another shape. Instead of one vector of size 10, we have matrix of size 2 by 5. And here, yeah, we see that view here wasn't in place operation, so tensor, the original tensor remains the same.
Can you put for your reshape -1 for the last dimension to show it? Like reshape 2, I don't know if it works for real. I never tried.
Yeah, so if it is possible to indicate -1 for one of the dimensions, and Torch will calculate automatically the rest. So you have 10 elements, first dimension is 2, then Torch automatically can decide that the last dimension is 5 because 10 divided by 2 is 5. Yeah, so we see 2 minus 1 is exactly the same as 2, 5. Thank you, Eric. Yeah, multi-dimensional reshapes are also supported. So you can, instead of having like 2, 5, you can have 2, 5, 10 if your original vector is of size 100. Another operation is swapping dimensions. So you have matrix like this, and you want to make it to look like this. Yeah, the transposition. So transpose does transposition for 2 dimensions that you indicate. If you do it with minus instead of like 1, 2, and you say -2 is like calculation, the order from the right. So -1 is the most right dimension, -2 is the second from the right dimension. Okay, so to swap 2 last dimensions, we call this thing. And we see that originally we had 2, 5, 10. Now after transpose, we have 2, 10, 5. Yeah, so we swapped 2 last dimensions, and the number of elements in each dimension also swapped. Also, it is possible to change more than 2 dimensions, but then we want to use permutation method, and we also indicate the new order of dimensions. For example, we want our actually first dimension to become last, so 0 becomes is on the last position. The first dimension becomes the zeros dimension, and the second dimension becomes the first dimension. Yeah, we have ordering from 0.
Just maybe give some context on that one, because the order that PyTorch will typically assume for dimensions is that if you're working with images, for example, height and width will be last, and then color or other batch will be before that. Sometimes when you want to view pictures, usually you have an RGB where you have the color at the last, those things like shifts. We need to do this.
Yeah, so usually images when you work in PyTorch have like batch size channels. RGB is like 3 channels, grayscale is 1 channel, okay, like height, width. But to draw these images, you usually want to get something like this. So you want channel dimension to become the last one, and to do this, you do permute 0, 2, 3, 1, like this, okay? And this permute will change such shape to this shape. Yeah, the common operation is to add extra dimension. To do this, we call unsqueeze method, which adds imaginary dimension to the first index. When we say imaginary dimension, the dimension size is equal to 1. So there is only one element in this dimension, so it just thin to make a proper shape. It doesn't actually do anything more complicated than this. There are many other functions, and PyTorch documentation is pretty good, so have a look on them.
After the documentation, also the forums are very good. Like if you normally just Google something, PyTorch XXX, you'll probably find some forum discussion which discuss what you're looking for.
Yeah, or Stack Overflow, all this stuff. PyTorch and NumPy have similar syntax, and you can do many operations on tensors in the same manner you did it for NumPy. For example, there are some aggregation operations like calculating mean or average, calculating sum, getting max element or min element. There is also such thing as dimension and keep dim argument. So dimension allows you, without any arguments, your mean is calculated over the whole tensor. But maybe you want to calculate minimum mean for over the first or the 0 dimension. To do this, you indicate dim equals 0, and note that now instead of getting one scalar, we are getting the matrix 100 by 1000. Our original tensor was 10, 100, 1000. We did average across the first dimension, and now we don't have this first 10 dimension, we have only the last 2. Or we maybe want to have mean around over first and 0 dimension. We can also do this. And now we are left only with the last dimension. Also, there is such thing as keep dim. It automatically adds imaginary dimensions to your tensor. So maybe you want to calculate average only over 2 dimensions, but you want to result in a 3D tensor instead of 1D. And you will get, using keep dim equal true, you will get torch size 1 for the first dimension, torch size 1 for the last dimension, and the one dimension which you didn't consider will be the same as it was before. You can calculate Frobenius norm on any other norm. There is also linear algebra in a similar way as it is in NumPy. There are 3 possibilities to do exactly the same thing. So one, to multiply A and B matrices, you can use A dot matmul B, or you can use A, I don't know how you say it in English, at, I guess, yeah, B, and instead of having like a method from A, you can use directly torch matmul A and B. And as we see, they result in exactly the same output. Okay.
Alright, this imaginary dimension. What exactly I should, for example, make this imaginary dimension?
So imagine you want to, the question is when we use this imaginary dimension. Here is an example. Maybe you have grayscale image, but you are given it, you have it in such format. You have height, width, and batch size. But in order to work with so-called convolutional models, when we will cover on Wednesday, you want to have you have to explicitly write that you have one dimension. One channel. So actually, to work with convolutional models, you need something like this. But you are given only this thing on the left. So you add imaginary dimension, and you have like here one channel. Okay.
So it's not about the value using that dimension, right? It is just the existence of the dimension.
Yeah. Imaginary dimension is needed only to get a tensor of a proper shape.
We're not adding any data.
Yeah. Yeah, that's why it's called imaginary. It does nothing, only like adds
Just adds dimension.
the dimension, yeah.
Which you need for convolution.
Yeah, moving on to automatic differentiation. Atli covered some of this, but let's look at this again. So Torch computes gradients automatically via backpropagation, this backward step. To do this, you need to create a tensor that requires gradient. To do this, you set requires grad equal true. Then you define some differentiable scalar function, whatever, and you calculate loss. Loss is equal to whatever from this tensor A. You request backward pass, loss.backward, and the gradients will be available in a.grad. So here are some text that at least one tensor from like whatever depends on several tensors, at least one of them should require grad equal true or you will fail. I guess we'll see it today. So here is example. You have x, we have y, which requires grad equal true. You calculate some z, x multiplied by y plus 10. You calculate some p to get a scalar loss value. You do p dot backward. And now you have gradients just by accessing x.grad and y.grad. There is such thing as detach. So sometimes you don't want to pass gradients through some of the tensors for some reasons. Maybe sometimes you want to like update only part of your model, and for instead of passing gradients to the whole model, you detach like one part, and the gradients will be passed only to the second part of the model. So a detach returns a copy of a variable through which backpropagation doesn't pass. What I wrote here. So sometimes if you save some loss functions in a list just to do logging or like to plot what was your loss value, you should detach this loss, because otherwise your gradients will be kept in your memory, and you will get out of memory, your hardware won't work proper, and so on. There is also in place version, which doesn't create a copy, but does all the same stuff in place. And let's see here. So we have the same function, but instead of saying So instead of y, we use y0 here. It requires dot equal true, and y is exactly y0, but after detach. We calculate the gradients again, and we see that y doesn't contain any gradient because we detached it. So only x has gradients now. Yeah, so it is also possible to, yeah. Yeah, but yeah, so you see, if you do request grad equal false, it will just say y grad is equal to none. But the problem here is that after you calculated some losses, you already calculated some gradient, and you want to store this loss value somewhere. You can't store loss directly because it has gradients. The gradients have use some memory, and you want to save memory. So instead of preserving directly loss, you preserve only loss detach, which has exact same value, but without gradients. So you don't waste your memory on saving gradients. I guess if you calculate loss and then set requires grad equal true, it won't equals false. It won't work. Yeah, and you can done like do something like loss grad equal none explicitly, but maybe you want to have one copy of loss which has gradient and one copy of loss which doesn't have gradient. So it's better to use detach here. Yeah, so it is important to reset gradients of a specific variable to using optimizer zero grad, as Atli showed in the last slide, and now we'll see why. Imagine you have two functions. One is x squared, and one is 1 over x. Their derivatives are written here. So if we do not reset gradient, the gradients will accumulate. They will sum, and instead of getting when we calculate gradient for the second function, instead of getting -1 over x squared, we will get 2x plus -1 over x squared. So let's see the code. We have x, we have y, which is x squared. We calculate backward. Okay, the first derivative is great. But the second one, we didn't reset the gradients here. Know that instead of getting dp over dx, which is equal to -1 here, we got just once, +1. And if we look carefully, +1 is 2 minus 1. Yeah, so gradients from this part summed with the gradients from this part, and we got wrong gradient. Now we reset gradient using grad 0 here, and now the gradients are calculated correctly. Okay, so that's why you need to use optimizer zero grad. Yeah, we have left only with 4 minutes. Is it okay if I spend like 5 times for 5 minutes more than? Yeah, okay. Thank you. Yeah, so for memory saving, gradients are stored in a so-called leaf variable. So your PyTorch has this computational graph. You have leaves, which are the first layer from this tree, yeah? And gradients are stored usually only on this leaf variable. And if you look here, you will see that your leaf variable x with requires grad equal to true actually has gradient, but some variables which were in between doesn't have gradient. They have gradient equal none. And PyTorch even gives you a user warning that you're trying to access gradient of a non-leaf tensor. So something which was in between. Actually, gradients are calculated for these tensors, but then they are removed like, to preserve memory. Yeah, and here's an example that I guess this is the same thing, but with two variables. And there is such thing as isLeaf, and you see that x and y here are leaf variables and z and p are not leaf variables. And not leaf variables doesn't have gradient. If you want to preserve gradient for non-leaf variables, you should call this method, which is called retain grad, before you do backward. So it's not mandatory to do this retain grad like directly here. The main thing is to do it before you call p.backward. So if you do retain grad, you will get gradient for this retained variable, but you won't get gradient for variables that are not non-leaf and you didn't run retain grad for these variables, like y. Y doesn't have retain grad and it still has a gradient equal to none. Yeah, know that you always have to have at least one leaf variable which requires grad equal to true. Otherwise, your code will fail. So here we have requires grad equal false, and we get an error. Here we have at least one leaf variable with gradients, so this thing will work. This also works, but we have another requires grad equal true. Here we have requires grad equal false, but write retain grad, sorry. And because even though we wrote retain grad, this will fail because the leaf variables have requires grad equal false. And note that W depends on Z. And even though X has requires grad equal true, we still get an error because W doesn't depend on X, it depends on Z, and Z has requires grad equal false. And finally, when we have Z with requires grad equal true, we can even use the retain grad and everything will work. Yeah, I will try to increase the speed. Yeah, so for datasets, you have two things in PyTorch. First one is dataset. Given some index I, dataset returns you xi, so the ith element of your dataset. And data loader is an object, iterable object that combines your data into batches. So batch B is equal to item number 1, and so on, item number batch size. To create a dataset, you need to create Python class. I hope you know what is Python class. If not, ask me later. So this class should be with a base class dataset here. You should define three things to create a dataset. First one is init, with defining some variables like all your data. Get item given some index returns ith element like this, self data index, and len returns the length of your data sets, the total number of elements. And here is an example. Imagine your whole data is 1000 elements of size 10, 1000 random vectors, and you pass this example data to your simple dataset, and do simple dataset 10 to return x10, so the 10th element of your dataset. As the total length of your dataset is 1000. Dataset, you just pass your data loader, sorry, you just passed your dataset to your data loader, indicate batch size, and now you can iterate over this data loader using for cycle, for loop. And we set batch size equal 20. So now each our batch contains 20 elements here. To access one batch, without for loop, we can use next iter or iSlice. Have a look at it at home. Like it doesn't matter much. You usually use this kind of stuff. Yeah, and finally, optimization. It's not mandatory to optimize only deep neural networks. You can optimize any functions in the same manner. And today we'll cover such case because it's much simpler, but shows the exact pipeline. So you have some function f at x, which looks like this. Your loss here is your, imagine you want to minimize this function f. So your loss here is just f at x itself. We will do one step of gradient descent using torch optim.sgd, stochastic gradient descent with some learning rate, also known as step size. And we will set xs to the updated value from the previous step, from this step. And we'll repeat this operation num step times. So here is our func. It looks like this. Here is minimum. We'll start from the random point and try to descend to this red dot. And usually your pipeline in a simple way looks like this. You have your current solution, some random value. You initialize your optimizer. You pass the things you want to optimize. For now, it's our current solution with some learning rate, for example, 1e minus 2. We want to do, for example, 200 steps. For each iteration in this num steps, we calculate loss. In this example, it's just func over current solution. We zero gradients because, as you remember, if we don't do this, we will accumulate gradients, and we don't want to do this. We calculate gradients via current loss dot backward, and we update our current solution using optimizer.step. And here are just some login stuff to visualize how it works. So let's see. Yeah, so you see that this green dot goes lower and lower from some random point. It gets closer to the minimum, and that's what we wanted to do. Let me restart from some other point. Yeah, so we see that this works exactly as we wanted to. And for and we found the minimum. And for deep neural networks, the pipeline will look exactly the same. So we will have to define our model. We will have to define a data set and data loader. We will need to choose optimizer. As Atli said, use AdamW. Here I also suggest Adam, but like use AdamW, okay? Instead of passing this current solution, you will pass model.parameters to optimize model weights. You should choose a scheduler, use cosine annealing with warm up. I would say one cycle, but Atli doesn't like it, so maybe don't use it. Yeah, one cycle also has this warm up technique. It's similar to cosine annealing, but with warm up, but different in details. Yeah, you should iterate over your data loader. For each batch, you compute the loss, do dot backward, run optimizer.step to update model weights, scheduler.step to update learning rate, and you must not forget about zeroing the gradients before doing optimizer.step, before calling backwards, so at the beginning of your train loop or after step. And you should also do some logging to see how good your model trains. And that's all your model is trained. Yeah, so as we said, the scheduler optimizer, you can use the ones we suggested. In general, the choice depends on the task. There is no such thing as that works all the time. You should try several settings, several hyperparameters, and so on, like tune learning rate, weight decay. Don't forget about the total number of training steps. But there is one thing to say, that if you want to reproduce some paper, you like read the paper and you want to do the same thing as you saw in the paper. Usually, to achieve the same performance as they did, you must use the same techniques that they use. So if they used HGD instead of Adam, use HGD. If they used like constant LR for some reason, use constant LR. But it's only the case when you want to exactly reproduce their paper. So usually you can use still cosine annealing instead of constant LR and achieve the same performance or even better. So you should not use the methods that we suggested only if you know why you want to do something else. Okay. Yeah, I wrote it also here. Yeah, so for today that's all. Sorry that I took 8 minutes more. We will have another lesson at 13 about Python and Git, which are essential for teamwork and for general development of proper code, because it supports versioning. And there are also some useful tips that will increase your performance for coding. And on Wednesday, we will cover the models like fully connected networks, convolutions, all the stuff. Like today, we only saw models as computational graphs, and we will look directly on existing architectures on Wednesday. Yeah, thank you all for coming. See you in an hour.